Hello and welcome to today's Smart Safety Connection Seminar. My name is Junseon Hwang and I'm a Safety in Transportation Fellow for Safety 21, a US DOT University Transportation Center. The Smart Safety Connection Seminar series is sponsored by Safety 21 as an opportunity for faculty to showcase their current transportation project. It is also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and foster future interdisciplinary collaboration. Please note that this session is being recorded and all participant microphones are muted. If you are joining us online, please send your questions through the chat, or if you are here with us in person, feel free to raise your hand. You do not need to wait until the end of the presentation to ask your questions. You are welcome to ask them throughout. Now, I'd like to introduce today's speaker. Professor Pingbo Tang specializes in civil infrastructure operations and human systems engineering with a focus on enhancing safety in transportation and construction environment. His research integrates remote sensing, physics-informed machine learning, and simulation-based risk analysis to improve operational safety and regulatory compliance. Of heavy-duty vehicle fleet by leveraging physics-informed machine learning, explainable AI, and data analytics. Please help me welcome Pingbo and Ava as they share their presentation, preventing high-risk crashes in heavy-duty vehicles with smart sensors and vision systems.
Thank you for having me here. Should I share my screen? Great. So it's my honor to share this work with this excellent group of audience here today. And special thanks goes to my research collaborators, Professor Yori Nakahira and Xi Yudeng from CMU Electronical and Computer Engineering, and also from our industry collaborator. Their support is very important for this work. Clearance Technologies, Truck Light, Safety Emission Solutions. The work is about the prevention of high-risk crashes of heavy-duty vehicle with new technology, and we're going to explain what are the new technologies. Why we are looking at this problem? This problem is significant because the transportation system defraud the delivery supply chain relying on heavy-duty vehicles. And the heavy-duty vehicles are also important for the emergency response and agriculture, mining, construction process, which is important for our infrastructure investment ongoing right now. 70% of the freight. The safety of a heavy-duty vehicle is important because it's usually involve fatality, and the number of fatal crashes in the United States is stable, but the percentage or the number of a crash involve heavy-duty vehicle is actually increasing. The main reason is because those vehicles is very difficult to control, it's very large, and because they are heavy and they have less data. We don't have enough data to understand their safety, and we have very, very limited information and about how crash happens and when crash happens and how much cost. Then this is some data we got so far. We have a lot of those real-end crashes, and we think about this and say, okay, real-end crashes seems like it's a big problem for heavy-duty vehicle. Then we dig into the data and we look at what is the amount of crashes involving the side crash and the real crash of heavy-duty vehicle. So this is a number. We can see from this table, of course, the front-to-front crash involve a lot of fatalities, but the side and real, it's the dangerous area also. You can see 510 from the rear and hit by the passenger car. And the side, it's a 281 hit by the passenger car. So there is a lot of those issues with the trailer, and not just the tractor. Tractor is the front part, the trailer is the end part. Then when we look at those big chunk of the trailer, and we realize that it's a very special physical piece, and it's not passenger car, which only has one piece. The heavy-duty vehicle has two pieces. The first piece is the tractor. The second piece is the one connected to it is the trailer. Then the physical constraint between the tractor and the trailer need to be properly modeled and simulated and to help us to understand why there is some kind of like a very difficult situation for those trucks to operating and to avoid dangerous situation. Then roughly, we classify the situation as avoidable crash and unavoidable crash. This is not a static classification. We're going to explain why it's not like a static classification, because the technology could make some of unavoidable crash become avoidable. Then unavoidable crashes usually has two major reasons: environmental condition problem, like a slippery road, like a very, very low visibility at night. And
Because
the vehicle condition
Zoom isn't on my work computer.
Okay. Sorry, we're muting them. It just
okay. So the vehicle condition is not perfect, and we need and sometimes it's just like we have a very bad vehicle, and which makes the crash unavoidable. Then for environmental condition, those are the examples. It has a book called Green Book. That's called Green Book. And they mention all those reasons the environmental factors can cause very difficult situation for heavy-duty large vehicles. And there are many crashes is related to the are related to the vehicle itself. And some sensor system and the safety programs, vehicle-to-vehicle communication technology, they are trying to help us to understand the environmental condition, the vehicle condition, and the collaboration between multiple vehicles to help us to understand when and how those crashes is going to happen, to prevent them. Then this brings us to the role of technology. And what are those technologies? As an engineer, I always produce those not so beautiful pictures. But it kind of captures what we are trying to talk about. It's an overview. We need to understand heavy-duty vehicle and what are the factors, and use those historical data to capturing those factors influencing the crashes, the occurrence of crashes, and what technologies they are available, and including the sensor vision systems, including the modeling technology, which means physics models, helping us to understand the physics behind those crashes. Then combining those together, we call safety system digital twin, and that means we have the data part, we have the physics model, and we want to use the data to update the model and to help us to do what-if analysis, to help us to capturing risks and also preventing crashes. Now, I'm going to hand over to the person who is really doing the work, Ava, who is going to show you these 4 pieces of work.
Team. So here we are trying to, first we try to analyze the crash statistics and understand, okay, what is the real problem. So here you can see that the proportion of different crash causes are shown in the pie chart. And most of those crashes are related to driver behavior and human errors. So this is a very significant area that researchers are looking at. But for vehicle failure that cause crashes, we have 10% of those crashes that just happened because of the vehicle failure, and 3% are because of the environmental conditions. So within those 10% of vehicle failure or vehicle condition, 29% is because of brake failure, which is a very significant and important component of the vehicle, especially heavy-duty vehicles. So here we can see that, for example, for brake pad thickness, we have the unit of 32 inches. And if, based on the regulation, it should be within 2 per 32 to 70 per 32 inches. And if it is less than that, if the thickness is less than that, then the brake will definitely fail. So here we analyze the heavy-duty vehicles crash causes, and we categorize them into three classifications. First one is vehicle-related factors that you can see. The most important one is brake failures. It could be overheating of the brake, it could be brake pad thickness, it could be some issues and failures to the brake disc. The second major component is tire failures. That could be tire blowouts, it could be the tire pressure issues, and it could be related to the tread of the tire. And the last one is poor visibility. It could be due to the lighting system of the vehicle itself or the blind spots that the vehicle has. So moving to the next factor or cause of the heavy-duty vehicle crash, we have environmental factors that we have weather conditions that, for example, in rainy condition, in snowy weather, or especially in foggy weather, driving will be very difficult. So the drivers will have less control on their vehicles. And regarding road conditions, there can be different things that can affect the crash or the actually happening of the crash. So it could be construction zones that we have a lot of those fatal and severe crashes in those areas, slippery road or the light condition of the road, or the uneven road condition, and also the congestion of the highway. So the other factor could be road design. It could be sharp curves or merging roads or the width of the road and other related road design. And the last one is the operational factors that tractor trailers, especially the large ones, have a limited maneuverability, and they have longer stopping distance in comparison to passenger cars, and they have load stability issues. So it should be somehow even. The load distribution should be even. It could affect the stability. So we introduced a term called near miss, and we want to know why we need to study near miss data, and what is a near miss actually. So crash data is based on the historical data, something that has happened already, and we can see that from different sources we have different type of crash data, as we said. Okay, the cause of the crash, where the crash happened, and what led to that crash. But there are some situations that are very rare, but they are severe. So we need to study those. And because of the limited and sparse crash data, it's hard to analyze the trend through through a period of time. And also they are reactive. So they happen, then we analyze them and study them. But near miss data is very frequent. It happens a lot of time in different scenarios, but we don't have any historical data available that says, okay, in this scenario we have this amount of near misses. And it's good because it predicts the risks before the crash happens, and it's kind of proactive. So if we mitigate and reduce the number of near misses, we can reduce the number of crashes and those fatalities. So basically, what is a near miss? Near miss is an avoided collision that could have resulted in a crash, but it didn't. Studying near miss is important because it reveals risky behaviors and vehicle vulnerabilities, and it refines safety technologies that will introduce different types of safety technologies, and it improves driver training and maintenance schedules. So we can alert the fleet managers or driver that what's going on real time on the road or related to the vehicle. So we have two major factors that we consider that they affect detecting and preventing a crash risk for trailers specifically. One of them is controllability, that it contains environmental conditions like the weather condition or lighting condition, and the other is vehicle conditions. So vehicle lighting system can affect controllability, drivers' field of vision, if they cannot see when they are moving forward, then they will lose their controllability. And also the load distribution that I just mentioned in the previous slides, and the vehicle maintenance. So for example, if we have some component failure like brake failures, then we'll definitely lose control of the tractor trailer. So in terms of visibility, again, we have this road condition and traffic condition, and we have some occlusions on the road, or even we have some, in some highways, they are very dark, and the drivers have this challenge of seeing what's going on the road. So, and also we have this speed, vehicle maintenance, load distribution, and vehicle design and aerodynamics, things that are involved in visibility of the vehicle. So we say that, okay, we can enhance heavy-duty vehicle safety with smart technologies. So why traditional safety measures are not enough? So because one of them is that human reaction time is delayed, and we need to alert the driver immediately. That's what's going on the road. And they also have limited visibility. So we may need some cameras or some sensors to alert the driver that what is in the blind spot, so that they can understand their surroundings better. And also inspections, vehicle inspections detect issues often after they occur, not before they occur. We have a lot of brake inspection violations, tire inspection violations on the road, that when we have road inspections that randomly capture vehicles, we can see that they have brake issues, tire issues, lighting issues, and so on. So how can smart sensors help? They will enhance driver awareness or situational awareness through computer vision and other AI and automated systems. We have real-time monitoring of vehicle conditions and proactive warnings for potential crashes that might happen on the road. So some of those or key sensor technologies for HDVs are vision-based sensors like cameras that are installed on the rear of the trailer or the side of the trailer that basically are the blind spots of the driver. And we have this LiDAR and radar sensors that can estimate the distance from the front vehicles and alert the driver, and also help the automatic emergency brake to just, when they see they're within a specific distance, they just stop. And then we have this brake and tire pressure sensors that whenever we have brake issues or the pressure of the tire is lower than normal, then they will alert the fleet manager or the driver. And also we have this V2V or vehicle-to-vehicle and communication and telematic systems that can be very basic, like just flashing lights, or using other sensors that can connect these two vehicles to be able to understand their conditions and communicate with each other. So based on the statistics, this automatic emergency braking as one of the technologies reduce rear-end crashes by up to 43%. And especially in heavy-duty vehicles, in another study, identified that it can reduce these severe crashes from 22 to 57%. And also, of course, vision and radar detect slow and stop vehicles, and so that they can trigger the AEB. And we have this tire blowout prevention that through predictive analytics, it alerts the driver and fleet manager about the failure before they happen, which enhance the mobility and, of course, safety of the vehicle. And near miss detection using some physics-based modeling and computer vision can identify the high-risk zones around the vehicle, and then optimize driver training and inspection practices as well by analyzing those close call events that are about to happen. For future of smart safety technologies, we have self-learning safety systems that adapt to new risks immediately, and also edge computing that can just make this real-time hazard detection faster. And we also have this idea of autonomous trucks that are not popular right now, and fleet managers basically prefer to rely on human drivers rather than autonomous trucks. But anyway, sensors are evolving to adopt and support those autonomous trucks as well. And also we have some industry adoption challenges and solutions. One of the most important things is cost barriers for small fleets that we also will talk about it later in the slides, that they need to just adjust and justify the cost that they need to spend on installing those technologies on their vehicle fleets. And of course, we have regulatory barriers that we need that standardized AI safety policies. Like, for example, we have this ELD from 2017 that all vehicles need to install this technology to estimate the number of the hours that the driver is driving. But it took time that they just regulated it and made all fleets to have this technology on their vehicles. So here is we propose the smart trailer definition, that it has different types of sensors on different parts of the trailer in particular. For example, we can see that at the end of the trailer there, we have this vision system that helps the driver to have a better understanding of what's going on in the back or rear of the trailer, which is the blind spot. And also, for example, in the tire part, we have the pressure monitoring sensors that immediately alerts the driver that, okay, your tire really needs to be replaced or needs inspection for the pressure. So, and other sensors like, for example, for the cargo or the temperature that can just adjust the temperature for the cargo that the trailer is carrying. So here is the safety system and digital twin framework that we have. So here is our physical system that contains the social context that includes the different population and different regions that are based on the population. For example, whether it is a rural area that we are studying or whether it is an urban area or large metro area. So we have 6 different categories for that. And then we have environmental condition to just capture what is going on in the surrounding of the vehicle. And we have a mechanical system that we have the deterioration model, that when the vehicle is going to deteriorate and which component is more prone to risk. And we have this technology adoption for the vehicle and even our fleet. So on the other hand, we have this virtual model that we capture data from physical system through computer vision and telematics data and all those sensor technologies. And then we just embed it into our virtual model, which is based on the simulation and physics-informed machine learning that we just simulate and model the behavior of those tractor-trailer system. So, and again, we go back to the physical system with OODA loop, observe, orient, decide, act loop. So we have this human feedback there, and it's just like a loop. We go through the physical system to the system twin, and then through system twin to the physical and real world system. So why physics-informed machine learning for crash prevention? Why not machine learning itself? Why it's not enough? Because when we use machine learning, it's based on a data-driven method, and we learn from historical data. So it might ignore real-world physics, so it will suggest unrealistic or unsafe predictions. For example, it will just ignore the angle that the vehicle can just, the driver can, the steering angle could be different, and the maneuverability could be just somehow unrealistic or unsafe. Also, it might lack certain but dangerous scenarios, but they are rare, so it will not learn and it will not consider those rare scenarios, although they are very dangerous and very severe. So it fails to generalize to new and unseen safety risks. So here we identified 4 different risky scenarios. That one could be the passenger car that is going to hit the trailer from the side. The other is the passenger car that can just go under right, we call it under right crash, that just, it's a rear end crash, and it can lead to fatality, a fatal crash, and it's very dangerous. The other is the merging roads that, for example, the tractor trailer is coming from a ramp, and the passenger car is coming from the other side, and they just merge together. And the other one is especially related to the maneuverability of the tractor trailer system, that it should just be able to pass through these sharp curves and turns. So this is our methodology that we are trying to simulate our tractor trailer behavior. It's called physics info reinforcement learning. And we have the vehicle state and horizon as the input. And then we have this model that you can see it has different layers. It's based on DQN. And then we have the loss function that captures the loss of data and loss of the boundary conditions and loss of the model. It combines these 3 components. And then we have, currently we have 2 control actions that adjust our steering angle and the velocity. And so, and this is the, on the right-hand side, we have this Carla environment, the environment that we simulate our tractor trailer system. And we just try this system in different and risky scenarios that we identified in the previous slide. So we have some initial results from our computer vision analysis that we applied to fixed cameras of Turnpike and PennDOT videos. That first we, within 1 day, 24 hours, we analyzed how many vehicles, and what is the proportion of the heavy-duty vehicles on the highway. So it's almost, or it's exactly a quarter of those vehicles are heavy duty, and it's I-76, if I'm not mistaken, from Turnpike video. And for example, we tried to have some behavior analysis of the heavy duty vehicles. So in terms of lane deviation, how many times or what is the percentage that the truck just deviates from the lane. It was again a quarter, and here is the speed distribution within 24 hours. So from other sides, we had this analysis because if you remember at the beginning, we proposed this question that what vehicle in what environment show more risky behavior. So to somehow answer this question, we analyzed some large and small motor carriers, meaning that if they have less than 30 vehicles in their fleet, so they are considered as small motor carriers. So we could look into those specific vehicles that are within small motor carriers to see in what age, what was the vehicle age that showed risky behavior, and in what region it was operating. It was being operated actually. So, and the results show that small carriers show much more risky behavior than larger motor carriers due to a lot of reasons that can influence their performance. So here is our analysis based on the vehicle age and the region that the vehicles are operating. So the regions are based on the population of that area. That could be like the red one is the large metro area, which has a very large population, and the non-core area, which is the green one, is like rural area. There are somehow no one is here, or they have less population. So the results from different years showed that actually from 2017 to 2021, consistently we have region 6, which is non-core area, as the critical region here, and the ages differ from different years that we analyze, but region 6 is the critical region that we have, and these are other probability of crashes of those vehicles in different areas within different age groups. Also from PIRL framework, we are trying to, the potential outcomes of our analysis is the number of near misses that we have for different scenarios that we defined. And we try to quantify the risks by computing the safety probability of different tractor-trailer distances from other vehicles so that we can understand what is the actual near miss. Because that near miss is not a fixed distance. It depends on the situation and condition of the road and the vehicle condition. And we try to identify the safety zone for the tractor-trailer for different scenarios, that in what distance the vehicle is risky or is safe. So in terms of implications for industry, we need to consider that what are the factors that affect the fleet performance. So one is, of course, the budget that they need to spend. The other is the workforce. Both of them can be considered kind of resources that they have. The other is the safety culture or technology adoption, that they just need to incorporate those sensors and technologies into their fleets. The other is the personal training, that if they have these technologies or automated systems, they need to train their driver or other workforce there as well. And they need regular inspections and maintenance for their fleet. So these are the factors that can affect fleet performance. But the barriers of these technology adoptions are the cost, especially for small fleets, because they need this justification. So one of the questions that we are trying to answer is that how can we customize these sensor installation for cost effectiveness? Because maybe it's not necessary for those, especially for those small fleets, to adopt a lot of technologies, all technologies that are there for their fleets. So we need to know that what vehicle has what problem so that we can install the specific sensor for that. And we have this data privacy and cyber security concerns. For example, for dash cams, the cameras that are installed on the dashboard of the vehicle, drivers are concerned about their privacy and they usually don't like it. And we have these regulatory barriers for AI-driven safety systems that we need to know that how can we just standardize or regulate these technologies so that all fleets just follow these instructions and regulations. And we also need to know that how to ensure these AI models and technologies remain explainable and trustworthy, so that they can convince fleet managers and other stakeholders that they are really helpful. So we just acknowledge our industry partners, Mr. Bernie Eller from Safety and Mission Solutions, and Mr. Paul Snigoki and Roger Riemann from Clarence Technologies, Trucklight, and our fundings from Safety 21, Mobility 21, Trucklight, Computation, and PETA, and just this is the conclusion that we have from an impact that our research can have on the society. So if we have these automated systems and sensors and this framework for our tractor trailers, then we can save a lot of those lives there. As you could see, there are a lot of fatalities that happens because of these heavy-duty vehicles. We can impact the social so it has social and policy impact on the workforce and driver well-being and other vulnerable road users like pedestrians, passenger cars. And it has economical impact, like you saw in the very beginning that a fatal crash of heavy-duty vehicle can cost up to $3.6 million. So if we can reduce the number of those crashes, we can save a lot of money there, and also we can enhance mobility and just by making them by having smart mobility and this connection between the vehicles together, especially the heavy duty ones. And thank you for your listening, and please ask any questions.
I was wondering, like, what influence do insurance companies have on requiring, let's say, the trucking companies to adapt these safety measures? Because I would think that if it reduces, accidents, it's going to reduce, insurance payouts.
Right. Yeah, actually, we are looking into this issue very recently, and we talked with Pitt, Ohio, which is a large motor carrier in Pennsylvania. They feel like there is this insurance implication, a legal implication of installation of those technology. But what they are saying is like sometimes they do not have data to prove it's whose responsibility, and the insurance company also don't have enough information to show, okay, how much we can save the cost with the installation of a technology. The data collection, it's a challenge, and some of those data is collected by survey, and by not by real like large scale motor operation data of the fleet. Then we cannot compare like a larger fleet with a smaller one, and we could also compare Pennsylvania with Chicago. And so the technology used for different environment might produce different benefit. And for insurance company, maybe they also need larger scale data to convince they implement a policy to say, okay, implement this, I'm going to give you a lower rate. Then, so that amount of data, from my understanding, is not there yet. And we need to try to push that button and to get more data, or use the physics-based simulation to prove some of those quantification of the risks. If we install the sensor, how much visibility we can improve and how much controllability we can achieve to reduce the probability of getting into those situations. Yeah, that's my personal perception. I don't have enough knowledge about insurance company.
No, go ahead first.
Okay, thanks. So I have a question about like different types of sensors. So due to physical limitation, the millimeter wave, like radar, can detect a longer distance, but are not accurate enough to detect short distance objects, while LiDAR can detect short range objects. But when sometimes it is close enough, it is already not enough, especially for
Heavy duty, yes.
So how is this problem addressed?
We don't have solution for that. I thanks for giving this very great like a problem statement. We do not know there is any like a automatic switch from the long range detector to the short range, and it would be great if we could have some. That's also my personal opinion. Like a satellite image might help us to, because right now the planet, they are claiming they have those video from the satellite. They could control, they could monitor the traffic flow and to see in what scenario the vehicle can get in close to each other. So that might be a solution from the top view, but from the ground view, you're right. If we got like a longer distance, the accuracy is not good enough. For short distance, it's high accuracy, but there's not enough time to react. Then the perfect solution should be long distance is also accurate, right? But if we have a vegetation, we have occlusion, and we cannot achieve that, especially in Pittsburgh, because if you make a turn and the signal is lost, then I don't know there is a solution besides a top view. Yeah, that's maybe audience has a better solution and more knowledgeable.
So great job, big fan of your work. So one thing I was curious about, actually it was a conversation we had with Raj earlier, was this idea of trucks have the trailer and the tractor, or the tractor and the trailer, right? So if I have a fleet of vehicles, am I investing technology like you're talking about in both the tractor and the trailer? Is it more realistic? Because sometimes the trailer is just like it comes off of a train or a ship, it's like a shipping container kind of thing, and it's kind of a dumb trailer, right?
Yeah.
So is that an issue where the smarts and the sensors and all the technology and the investment is going to be in both the tractor and the trailer? Is it just going to be, because my thought is it can't just be the trailer that has the intelligence, and also the tractor needs to have that intelligence. So it's a system, right, of those two things. So I guess it's if I have a fleet like Clarion is working with fleet companies, am I investing in both? Am I making sure that I first have the tractor that has all of that technology and then I worry about the trailer? Like, is that part of something you think about? Is the intelligence of both the tractor and the trailer, is one more important than the other?
Yeah, it's a very good question. My understanding is that Clarence, they are trying to push from the tractor to the trailer.
Right.
Right now, most of the fleet, they are starting to think about the tractor intelligence.
Right.
But Clarence, look at the horizon. They are seeing there is an opportunity for trailer intelligence. Number one, the number of trailer is much larger than the number of tractor.
Right.
Number two, there is this even though it's dumb, but there's a lot of dynamics problem, and there's a lot of chance for us to save energy by optimize the trailer operation, because the trailer is very heavy. The distribution of the cargo.
Right,
the distribution of the cargo might influence the operational energy, and also the tile of the trailer influence how much gas consumed by the tractor. It's a strong piece which can influence the energy consumption, and but the challenge is it's a fragmentation of this industry. The trailer belongs to different owner.
Right.
And
exactly.
who is going to invest? Is the owner or is the
And I'm also wondering, like, it was interesting, the statistics that you had, Ava, about it's these smaller, less than 100, right, fleet that have most of the accidents, right? The small carriers they account for more than, but they are the small carriers that count disproportionately. So I think that's something too. I'm kind of wondering, like, are they investing in smart? Like, are they? Yeah, no, they're not. I guess there's the answer.
It's cost justification that they need to have.
Yeah, then the owner of the trailer might, but I don't know. Maybe back to the insurance question. Maybe the trailer also has insurance.
That is something to think about. And then the other piece that I think I heard is that in China, they're not making a distinction between tractor and trailer. That they're actually putting them. They're all in one piece. So it's just one piece. It's a truck that has a tractor and trailer all together for shipping. I don't know if that impacts the work that you're doing. Yeah.
Is that going to influence the flexibility?
Right.
Of
Exactly.
operation? Because the tractor belongs to motor carrier, trailer belongs to whoever owns it,
Right.
and you are going to ship it
Right.
at the from Hong Kong to Los Angeles, then the trailer does not belong to the motor carrier in China, right?
Right. Yeah, it's very interesting. And then the idea of like long haul versus short haul, like that economic decision too, because you guys focus mainly on the turnpike. Was that most of your research was focused on the turnpike, or did you also look at like short haul or small,
Yeah, actually, we just analyze the videos that we could just capture from Turnpike, but we are also trying to collect some data based, with the sensors that we install on the tractor trailers, that they will just have some maybe shorter routes.
Yeah, we are trying to reach out to some motor carriers to see if there's any benefit to install the cameras on their trailer,
Right.
and to understand the operation environment of their trailer and where those damage come from, because sometimes they see the damage on their trailer, they don't know where those things come from.
Right. They just get out of the truck, they're like, oh, I didn't feel that. Pitt, Ohio, they're a deployment partner of Safety 21. Have you had conversations?
Yeah, we're working to show some of these to Pitt, Ohio, and to see to what extent they feel like these are some information they feel useful.
Right. Great. Thank you. Oh, good. More questions?
How small is small? Like, I think this is very basic. I don't know this. Like, what counts small or not?
What is a small motor carrier?
Yeah, based on the definition, the ones that have less than 30 vehicles in their fleet are considered as small. And I guess more than 100 vehicles in the fleet are like larger. Something in between.
Like, do you have the size? Like, what does the mass? But like, do you have like approximate like? I think.
No, just the number of power units that they have.
Oh, the number of tractors. Yeah.
Oh, okay.
The number of tractors. Yeah, is that right?
Yes.
Tractors. Yeah. The number of engines they have.
Hi, Ava, thanks for the presentation. So I had a methods question. So since near miss events are not observable, what do you use as your ground truth? Do you manually label the video feed?
Oh, for here, actually no, because we just analyze some behavior of the vehicles there from computer vision analysis. But then we realized that, okay, we need a definition for that near miss so that we can just compute that distance and detect and just count it, okay, whether this is a near miss or not. That's why we are just trying to simulate the tractor trailer behavior in a simulator called Carla, so that we understand, okay, for different thresholds like 2 feet, 3 feet, 4 feet, what is the safety probability of that tractor trailer model? And for example, if it is more than 95%, then it's safe, and then we just decrease that threshold. So maybe that decreased threshold is a near miss. So based on that safety probability, we understand, okay, this is a near miss, and then for that specific scenario, we, based on the data collected, we embed it to the computer vision algorithm, and then we quantify, okay, what are the number of near misses that happen in that situation.
Yeah, it's a very interesting question. We call dynamic safety zone, because right now the regulation says, okay, this is the distance. If it's closer than this, then it's a violation of the regulation. And we are arguing for different type of vehicle in different scenario, so that number should be different. And that real number should be the probability of getting into trouble. Yeah, then the physics-based simulation is trying to simulate the probability to understand for different scenario, different type of vehicle, even different distribution of the cargo in the trailer, how that influence that required safety zone.
So I'm not super familiar with how much energy the sensors would require on the trucks, but would that reduce the fuel economy of the truck at all, or where is the energy coming from?
The active sensor LiDAR will consume a lot of energy. The passive ones like a camera may not as much, but I don't think we have a benchmark study yet to study how the investment of sensor would influence the consumption of the operation energy use of the vehicle. However, we do have some study to understand the relationship between the tire performance and the gas consumption. And we also understand the relationship between installing the guardrail, and with guardrail means like the protection on the back side and the side. It's heavy, and if it's heavy, then you need more gas to move it. Then there's a cost benefit study on that. So the sensor-wise, I think the energy consumption, I don't know how significant it is. Do you know? I don't know.
Sorry. So building on the economy program, would you say that the infrastructure side is also at a good position to like embed some sensors? Because as you mentioned, LiDAR is still very, very expensive right now at this stage. So is it a good idea? Because I know both speakers have civil and environmental engineer background.
So you mean embedded sensor on the pavement, on the bridges?
Yeah, like crossroads. Would it be a feasible idea instead of like having all the burden on like the driver and their trucks?
So for infrastructure implementation of the technology, structured health monitoring research has been doing a lot of work for putting the sensors on the site, and also someone even developed like a new material for pavement to sensing how many vehicle has been going through on top of the pavement. I think the cost is still very high for those implementation. Another challenge for Pittsburgh and Michigan could be like using those technology in very cold region might consume too much energy yet, and where those energy come from and how to keep them on to 24 hours, 7 days, that's a challenge. It could be we need to find a way to balance the mobile sensor and the fixed sensor, and even like a Professor Jim Garrett, who has been doing like 20 years ago, he has looking at the use of mobile sensors to estimate the health of the structure based on the vibration interaction between the bridge and the vehicle, and they look at the vibration behavior. Just use the mobile sensor to understand, to eliminate the requirement for installing sensor on the bridge, because they think if I'm walking on this bridge and I feel that this bridge vibration, I feel it's not normal, then myself can tell this bridge is a problem. I don't need to put a sensor on the bridge.
If you're feeling it, it's too late.
I mean, like a robotic feeling and a human feeling might be different. Robotic feeling can see those like a millimeter level thing, and a human might not be able to.
That's true. Are there any other questions?
Thank you, Pingbo and Ava, for sharing your work. And to all of today's attendees, thank you for joining us today. Today's presentation will be posted on the Safety 21 website What's Happening page, along with a link to the video of the session. For students who are interested in engaging in transportation topics, the Transportation Club on campus is a great way to plug into transportation topics with fellow transportation enthusiasts. Thank you for attending our Smart Safety Connection seminar. We hope you will be able to join us again for our next session. In the meantime, please feel free to contact us with any questions. Thank you.